Now that we've looked at parallel and series circuits and some of the ways that we can analyze those, let's look at a mixed circuit. So in this question, this is the example that you'll see in the lesson. We have two paths. So this is one path. And it goes through one resistor. And then the second path will go through the second resistor and the third as well. So we have, like right here, we have two beside each other or in series, and those two in series are in parallel with that one. So we'll have to analyze this a little bit differently. So what we'll do is we want to simplify it, and we can find an equivalent resistance. So we can treat this as one resistor is what our strategy is going to be. So we want to find, in this problem, it's asking for the, sorry, I'm just going to look at my problem, the current through the battery. So find I through the battery is going to be the total current. So we don't know an awful lot here. We know the voltage of that battery, and we don't know the current, but we know some resistances. So what we're going to do, if we know the voltage is 15 volts, we want to find that current. So that's what we're looking for. We're going to use the resistances, and then we can use Ohm's law. So just as a reminder, Ohm's law is equal to V is equal to I times R. Or if we rearrange it to find I, we'll have move the R over. Since it's multiplied on this side, when we move it over to this side, we'll have to divide it. So another version of this is the current will be equal to V over R. We just need to know what that total or equivalent resistance is. And we've got some ways to find that. We can use our laws, Kirchhoff's laws. So just as a reminder, it's good to have them handy, but I'm going to just put a snapshot of those laws on here. So we can use our rules that we have here to find our resistance. We want to find the equivalent resistance of all of these. But we're going to start off with these two beside each other in series and just look at how to find the equivalent resistance for these two in series. To do that, whenever resistors are beside each other, I'm just going to put a little S here for series or in series. So I'm looking at the resistance of 2 and 3. I can just add their resistance and I get an equivalent resistance. So that is 33 ohms plus 44 ohms, and that will give me an equivalent resistance for these two of 77 ohms. So I've included those two together. So my circuit, if I could redraw it, would look like just having two resistors, this one here and those combined, and I can redraw that. So now I found that resistance of these two, and I could write that as one resistor of 77 ohms. And I'd still have this first resistor here as 22 ohms, and I still have my voltage. We sometimes call that the voltage supply, the total voltage, or they have V0 here. Either all of those are fine, and we know that. So the last thing we want to do is find the equivalent resistance between these two. So I've combined one. I just need to combine these two and I can have my overall resistance. But these two resistors are now in parallel. So when I come to my rules up here, I'm going to need to use this formula for the parallel resistors, and I will then find the equivalent resistance of that, and when I know the equivalent resistance and the voltage, I can use Ohm's law to find my current. So I've got my equivalent resistance formula written down for the parallel circuit. Let's sum in the values. My two values for resistor, the first resistor is 22 and 77. So I'll just keep this 1 over RT, and for resistor 1 I'll put 1 over 22, and for R2 I'll put 1 over 77. And then I will simplify. I'm just going to take my calculator and divide those. I get 0.045455. I like to keep lots of extra decimals here. And for the second one, I get 0.012987. So when I add those together, I get 1 over RT is equal to 0.05844. And we want to find RT. Right now we found 1 over RT, so we're going to use our little trick. We can flip this side, but we have to do the same to this side. Unfortunately, there's no fraction here, so what I'm going to do is be a little sneaky and put an over 1, and then I can flip both sides, so I get RT over 1 on the left-hand side, and on the right-hand side I get 1 over 0.05844. And that gives me 17.1 ohms. We are almost done at this point. The last thing that we need to do is use Ohm's law now that we know the total or equivalent resistance for this circuit, and so that we know, and then we also know the voltage is 15. So let's make a little room, and we'll finish off by taking I is equal to V divided by R. So in my final step, I just want to take that version of Ohm's law where I can solve for current, and I'm going to take I is equal to V, or 15 volts, and divide it by R, which is 17.1 ohms, and the final answer is 0.08766, but we'll round to 0.88. And the units for current should be amperes. So even though my voltage is in V, resistance is in ohms, our final answer is in amperes, and we will do a statement. So we'll just say therefore, so these 3 dots mean therefore. I like to use a therefore statement. It just saves me a little bit of writing. Therefore, the current is .88 amperes. And that's how you find the current of the entire circuit. That's usually your first step. You want to look at the whole circuit with an equivalent resistance. Sometimes they will ask you to go back and find the current in each of the paths of the circuit. So if they do that, what we'll do is we'll keep this overall total current. I'm going to write it up in both of the circuits that I've drawn up here, the simplified one where the series are put together and the original one. Now we'll start with this simplified circuit here and find the current in each of these two paths or two loops of that circuit. I'm just going to get rid of some of my work down here so I have some space. Since we know this circuit is a parallel circuit, I'm going to take one piece of information for a parallel circuit that makes it easy to keep solving for the others, and that's that the voltage in each path is 15 volts. So if I have a total voltage of 15, the voltage through resistor 1 is going to be 15. The voltage through resistor 2 is going to be 15. So we do know our voltages for each of those. Because the voltage rise for the battery has to be equal to the voltage drop in each path. And then when I know the resistance and the voltage, I can use my Ohm's law formula to find current. So for each of these, I'm just going to take my I is equal to V divided by R. So for resistor 1, I is equal to V over R. And if you do that, you'll sub in 15 volts and 22 ohms, and you should get, for that one, 0.68 amperes. For the second circuit, I2 is equal to V2 divided by R2, and that's going to be 15 divided by 77, which gives me 0.19 amperes. And I've almost got back to the original data. So let's write down what we know in our original circuit over here. I now know that this current going through this first resistor is 0.68. And the current going through the second resistor that we combined, and that is 0.19. Because the current for this whole loop has to be the same, the current going through this resistor will also be 0.19. Whenever there are resistors in series, then the current will be the same through both. It's like traffic on a road. If the cars in front of you are only going one speed, then the ones behind can only go the same speed. So when they're right in a row, the flow through them is the same. The last thing that we want to find is the voltage of 2 and of 3, because we know that that voltage here is going to be 15. But because there are two resistors, that voltage is going to be split. The drop is going to be split. So in series, the voltage drop will be split between two different resistors. So an easy way to do that is if we know I and R, we can use Ohm's law to find voltage of 2 and voltage of 3. So the last thing that we want to do, and maybe just to distinguish this is the voltage of 2 and 3. Let me just rewrite that. So over here, this voltage right here was the voltage of both resistors 2 and 3. And now that voltage is split between two of them. We want to find out what that is. So the last thing I can do is take my V equals IR and V2 is equal to I2 times R2, which is equal to 0.19 times 33. And that gives me a voltage of, so I'm just going to get my answers out, 6.4. And then I can do the same for voltage 3. And that's I3 times R3, which is 0.19 times 40 or 44. And that should give me 8.6. Just note, some of these don't have as many decimals. You can keep a few extra decimals. In this case, you would have 0.1948 if you kept a few extra decimals here for this current, and this one up here would be 0.6818. So they would add together to be 0.88 when you add them together. So a quick double check, the currents between the two paths, I1 and I2, is 0.68 and 0.1948, would give me the total current, which is 0.88. The voltages here are 6.4 and 8.6, which add up to 15. And the voltage here is 15. So you can do a quick check when you're done. And that's how we can analyze the circuit. We want to focus on at the beginning, though, joining any and getting it down to one equivalent resistance so that we can use Ohm's law.